Heap overflows, and this is good, clean fun. The simplest heap overflows are simpler than buffer overflows. Then it can get more complicated, but it doesn't have to be very complicated. So the issue of a heap, remember the stack has these stack frames, and it is carefully organized with this last in, first out structure, so you can use it to call subroutines, and for your subroutine to call another subroutine, and then for you to return. Heaps are when you have other uses for temporary storage of data. Like you're going to have a connection to a network card, and all these packets are going to come in, and you have to stick them someplace, and then process the data, and then you're done with it, and you want to empty out that memory to make it available again. So that's what you use a heap for. You allocate some room on the heap, you use it, and then you free the room on the heap. And this is how you can have a program that handles large things without having an unnecessarily large memory footprint to load it. That's the game. So you can see where they are with info proc map. Let me just get this stuff up here live because it's good, clean fun. And we're here. All right. All right, so let me get the first demonstration is the one I showed them in RSA, in fact. And that, I'll use that one now. Let's see, can I make this a reasonable size? Yeah, that's probably all right. So, must have been a different machine I was using. Let's see what's in 127. All right, here's heap 1, good. Let's try heap 0. Okay, nano, heap 0, dot C. Oh, all right. Control C. All right, Control X. I must have other windows open. No. Well, how rude. It's being edited by another window, but I can't see it. How rude. All right, let's just log off and see if that makes things any better. Get a lot of these goofy things. All right. Right. Okay, and let's see what's going on now. All right. I could probably show the processes and stuff. Let's just try restarting the machine. This is a Microsoft solution. But I just want it to work without bothering me. All right. Now, while that's happening, let me see if I can get that window to be some reasonable size. I know what's been going on. I've been projecting my stuff on strange projectors and getting resolution set to something stupid. Okay, let's see. Whoops, whoops, whoops. That's no good. Root. All right. If it continues to harass me, I'll just try and copy the file, work on a copy if the first one is somehow locked. Okay, let's try continue, see what happens if I just continue. Yes? Okay, anyway, it's letting me in. I have somehow created some kind of abnormal condition in my windows. All right, so here's a heap overflow that is carefully designed to make it very easy. So what I've done here is I've made a data structure, thing called data, that has a text variable called name, followed by a pointer to called FP. And then I have a function here called winner, which is what you want to hit, and a function here called no winner, which is what you don't want to hit. And then it maliciously uses this. It allocates a object for a data and file pointer, and then it sets the file pointer to no winner, and then it copies a string into the string part, and then it tries to execute the thing pointed to by the pointer. That's the point. So what's going on here is, at this point, it sets the file pointer part of this data structure to point to no winner, and here it executes that function. And since we have a argv1 is the command line argument, there's no length limitation, I can have an argument that's longer than 64 characters, so it overruns the data and replaces the file pointer. So it will be obvious that if I put in something more than 64 characters of data, I will change the address of the next thing that runs. That's why this is a very contrived example to make the exploit easy to do. And this is the first one to try. And this is very much like the first overflow you did in C, where you had two variables, and the second one was used for a bash command line command, and you could override the first one, and the text you put after the first 40 letters would be executed. This is the analogy. The only thing is it all happens on the heap. So you compile that thing, heap 0 and heap 0.c. All right. And you get a warning telling you this looks kind of evil, but it doesn't refuse to go. And so now I can run it, 0, and I can run it with hello. And then the hello is not too long, so level has not been passed. But if I do this, if I run heap 0 and I put in more than 64, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 30, 40, 50, 60, 70, 80, then I get a sed fault because some of those A's get in the pointer and it's going to crash. So now you want to debug it with your good old GDB. All right, and now I'm going to list. Okay, I didn't compile it with symbols, so I can do it, might as well go and do it in binary the way we should. Let's disassemble main. Okay, so here we go, starting main. Now down here is where it allocates something. Remember when you're reading this stuff, if you don't like reading assembly, just look for the names. This is sort of like you can't read, so you just look at the pictures. But that's not terrible, it's better than nothing. So malloc, we know we're gonna allocate something with malloc, then allocate something else with malloc. Then over here, there's a printf, which prints out that message. And here's a string copy. This is where the overflow happens, where you copy the input variable to the thing that's going to be too big. And then you call some function down here. So we'd like to see what happens to the heap here, and we'd like to find out what happens before and after that overflow. So I'm going to break before the string copy at main plus 115, and then after the string copy at main plus 120. That should work. So you break main, I might need a star, I think I do, star main plus 115, yeah, and then plus 120. Okay, and now let's just try this. If I do run and put in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and just 10 of these right now. Okay, it's going to go to the breakpoint. Now I can do info proc map, and it will show me the structure of memory for this process, and it's a little prettier if I make my window bigger. Let's see if I have to. All right, there we are. So here's the heap. That's all I was looking for. The heap is from there, from 8,000, 3,000. That's the start address up to 24,000. Okay, so let's look at the heap. I'm just going to copy this start address. Okay, and then let's do x, say 40x, starting at that address. And there's the heap. And I expected to see my AAAs on here, but it's not going to happen because we haven't done the copy yet. We've allocated memory on the heap, but I stopped it before it does the copy to put that data on the heap, so I need to continue. What's that? You should put 10 A's on it. It'll only be 10 right now, supposedly. So I should be able to see them up here on the heap, and there they are. See them up here, 41, 41, 41, 41. There, 4 of them here, 4 of them here, and 2 of them over there. So there's my A's on the heap. And of course, right now, it's not going to crash or anything. If I continue, I'm just going to get level has not been passed. And this is, I got this, I think, from some CTF, where they make it run like a video game. So now, let's run again with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10, 20, 30, 40, 50, 60, 70, 80. All right. And now, I'm going to continue because I want to get to the copy. Well, actually, let's look at the heap now. There.
It has the same memory next time when you run?
Yes. It's the heap address is specified by the compiler and the loader, and it'll be the same every time. Yeah, that's an important point. So the A's are going to appear here, and someplace down here is going to be the address, and that looks like it's probably about there. Someplace down there is the pointer to code, and that looks kind of close to it to me. And so now if I continue, and now look there again, now I have a lot of A's filling up a whole swatch of memory. And now if I continue again, it crashes. And this is the extended instruction pointer, AAAA. And if you don't remember that, you can find out with just info registers, showing you that right now EAX is full of A's and EIP is full of A's. Now EAX is interesting, and sometimes you can figure out how to exploit something in EAX, but when you have EIP, that's all you care about. So now I know some of those A's went right in the instruction pointer, and that's all I need. Because then I can just put the right value there, and when it goes to the next instruction, it'll execute the instruction I want it to. So I just need to figure out what part of it did that. So as usual, you just have to run a more carefully crafted exploit. So let's take 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and put, there, if I did that right, that's still 80 characters, but they're non-repeating at the end. And so start from the beginning, running that junk, continue, and then examine the heap. Okay, and that's what I thought. Here's the 41s, and then you have 0, 0, 0, 1, 0, 2, and so on. So now if I continue some more, it's going to crash, and it crashes with 0607 in the EIP. So now I know what I need to do. I need to take this and put my code where 0607 is. So I'm going to copy that.
Wait, what is 0607?
0607 is in the EIP. It crashed because it tried to execute this instruction. And this is 0607 backwards in ASCII. 41 is capital A and 31 is 1. 30 is 0. So now I know the 4 bytes. The last 3 on that line and the first byte on this line are the 4 bytes on target. So I need to write an exploit code of some kind because it's not going to be simple to do it here. So I'm going to open another terminal. Okay. I'm in the same directory, so now I can nano HE1, I'm going to call it. Okay, and put in slash bin slash user bin Python. I think slash user, right? That's how you do it, ain't it? I'll do it a million times. Hopefully I got it memorized. Then import. I don't really care about the carriage return. It's not going to do any harm, so I think I can just set attack equal. I can even just print it. Okay, let's be completely sleazy. There. That's kind of ugly. All right, I'm going to do that in a less ugly way. Let's have a attack equal this. And it was 0607 I care about. So let's put in everything up to 0607 there. Okay. And now, just kill it. Okay, attack plus equals. And now here's whatever I'm going to put in there, which I'm going to put in right now BCDE, just to make sure I'm right. And then just print attack. That's all I have to do. So that's now hopefully the BCDE will end up in the instruction pointer. And that'll do for the moment. So this is my .he1, and I make it executable. And if I run it, it prints out that junk, and that's good. So now I go back to here, and this time, okay, I run. I think that'll do it. I think this should do it, but we're going to see.
No, I got it mixed up.
I think that'll run. We'll see if it runs. Then I started from the beginning. Okay, now I continue. And now I look at the heap, which is here. Okay, and there's my junk, 41s, and down there is 42, 43, 44, 45. And if I continue, it hits 42, 43, 44, 45. That's B, C, D, E. So now I just need to figure out what I want to run. So let's go back and disassemble main again. And we've been here. That was pretty boring. Down here we got to the string copy that overflowed it. And then we're going to run the functions. Remember, there's a function called winner and a function called no winner. So we got to see that. Let's disassemble winner. There we are. So there's winner. Obviously, this is the address I want to run. Now all those zeros make me a little nervous. Are they going to work? I think they will terminate a string, and this attack does come in the form of a string, so I'm thinking I'm going to have a problem here. And let's go back to my instructions and see if I have fouled something up here. This is the very simple heap overflow is what we're doing here. And when I did it here, I found no winner. See, this address didn't have any zeros in it.
Can you just surround your output with double quotes in GDB?
Surround.
Your output with double quotes, a pair of double quotes.
Well, yeah, but see, the problem is I think zeros will terminate the string in a command line argument, and so they won't get in there. That's what's troubling me. So when I did it before, finding an address to inject, I disassembled it. Yeah, last time I did it, there weren't any zeros in it. It started 8040. You know. I think I've destroyed my machine. This happened to another student. He had nothing but zeros. It's because I just upgraded this thing to 2016.2. And something is wrong with Kali 2016.2. It does this. Here's we're starting all at zeros, right? It's amazing. They broke GDB or something, yeah?
I was running that same issue and I was wondering what the heck I was doing wrong. And so I pulled down the light image, and the light image seemed to work.
Right. And this one was fine, but I upgraded it to 2016.2 for another class because they broke something else all important in 2016.2. Whatever Takeshi was doing. He was doing something.
My Kali when I updated to 2016.2.
Yeah, there's something else wrong with 2016.2, something else really important they broke, and you have to go through a whole different process to fix it. So I think 2016.2 is pretty buggy stuff. So let's go back to something older.
So in this case, can you write a jump instruction on the stack, on the heap, and just point to that newly written instruction and let it jump to that function you want to write?
Yes, in principle, yes, that's right. You could do that. You could springboard, but it would be tricky to write that instruction because you can't refer to this address exactly.
Yeah.
You'd have to write code that doesn't have zeros that adds up to it. So I have this one, and I think that's 64 though. Here's a 2.0. All right, we'll use 2.0. And so watch it. There are definitely bugs in 2016.2. 2 or 3 students, and now me, have had trouble by using 2016.2. All right, so let's make dir 127. All right, and nano heap 0.c.
It's from apt upgrade.
I did the upgrade, but I think he did download. And still, the 2016.2, you couldn't do any of these projects because the virtual relative address of everything was all zeros or something stupid. It's
You could make the exploit work, but you couldn't see, like...
no, it won't work because the first zero terminates the string, so all the future bytes don't go in.
You can't see it because the strings.
And that means not only you can't see it, but the exploit doesn't work. When you try to inject code, the code doesn't go in. You can only put in 1 0 and it has to be the last byte. So you have to write a more complicated exploit. Anyway, I guess I'm getting it from curl, huh? Okay, thought I was going to be copying and pasting, but let's just do this. All right. Okay, Control X. See if that junk copied. Well, good. Copy and paste works anyway. That's something. Okay. And the compile failed. Undefined reference to main. Ooh boy. Well, let's see what we got here. Well, that's a problem. So maybe I'm not on the internet. I am. All right. It received 0, no route to host. The curl failed. Right. Is my server down? By the way, DH client doesn't work too well anymore in Kali either. Maybe it will in this old version. I find the only way to get on the internet is to go down and up. And then up. And see if I can ping my server yet. Oh, my server's behind Cloudflare, isn't it? And Cloudflare is probably dying today. So let's try this. I can go there directly. I think I can if I do this. No. All right. I'm getting hosed here. Let me see what happens if I get rid of the virtual machine out of the equation. And let's see what happens here. I want to say it's much better to fail here than it was at RSA. At RSA, I failed a couple times in my demo, and people are sort of don't seem to have a sense of humor there. Anyway, what's going on here? Fansclass.info. Okay, it's there. So when I can't ping it, it's just lying to me. Let's just try doing the curl out here.
It's not resolving to the right IP address.
What's that?
It's not resolving to the right IP address in your virtual machine.
Yes, it doesn't seem resolving at all or something. So I don't know what's going on there, but let's see if I can get it to download anything here. Good. Now I can nano it here. All right. Now I can copy it. I guess I'll have to do it in a couple of stages. So let's get everything up there, up to main, okay? Copy, fine. All right, nano heap 0.c. Okay, then let's go here. There, get the rest of it. I don't really need the internet to work for this demo to work. There. All right, fine. Let's try that and see how it works. Now let's see if this junk will compile. I should have a good GCC command back here somewhere. There it is. Okay, now /heap 0. Good. All right, so we're back on the road. Now let's see if GDB is going to cooperate. Now let's do disassemble main. And I was about one, okay. So here's the print, here's the string copy. So now it's +99. Remember, as you use different compilers, you get different assembly code. So by the way, one of the common mistakes a lot of students are making in the projects is they put in exactly the addresses out of my instructions. And they keep changing, everything. You always have to disassemble your code. Notice how it was +135 and +140. Now it's +99 and something. This is normal. They keep changing everything. So when you compile the same code again tomorrow, you get different assembly language code. There are many assembly language sequences that will accomplish the same thing. So anyway, now I want to put a break before and after this string copy, so it's main +99. And then it's main +104. That'll do it.
The star is for dereferencing?
The star is for indirect, yeah. It means this address, yeah. And so now I run with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. I think I'm just going to go see here. 1, 2, 3, 4, 5. That's 60. There. That should do it if I did counted that stuff right. Now I hit a breakpoint. Now I continue. And I'm just going to continue again. Good. Now I hit the 0607 again. All right. Now my life, I'm getting back on track here. So I need that string. I need a new. Whoa, look at this messed up. File edit, view search. You just get different weird bugs. There's no choice of an OS without bugs. You just get to choose whether you want the fatal bugs or non-fatal bugs. All right, so now I'm going to nano heap attack 1, user, bin. By the way, it's supposedly more professional to do this than user bin Python. Anyway, I'm going to use user Python. I'm sure that'll work. If you have more than one version of Python installed or something, that follows up. Anyway, A equals that thing, and get rid of the 0607. All right, now I'm supposedly ready. A plus equals B, C, D, E, print A, chmod plus X, heap attack. Okay. All right, now, if I go back to here, I can run. Okay, and now I'm going to start from the beginning and just continue and continue. And it terminated with a seg fault and didn't do what I wanted. All right, so let's stop at some of those breakpoints and see what I did wrong. There's the first breakpoint. I'm going to examine the heap. Try to do info, proc, map, the heap is here, which is a different address than it was before. And by the way, notice everything's now 8048. That's going to mean my addresses don't have zeros in them, and it'll work. That other thing, starting with too many zeros, fouls everything up. Maybe it's a security feature. Anyway, so now if I x 40x at that address, okay, I see the heap. Now if I continue, it crashes. How rude. All right, let's go back here. I heap at 1. Well, I don't see anything wrong with that attack file. Let's see, this is something that happened to me at, yes. These things are not both in the same directory. That's what happened to me at RSA. So, let's see what's going on here. That's in my home directory. Okay, so I need to move heap star to 127. Okay. So it couldn't find the file to run it, and that's what created the problem. So now, I've got the heap attack and the heap all in the same directory. Good, let's try it again. And I mentioned before, there's a lot of trial and error in this exploit development stuff. Even if you're more professional than me, you still do a lot of getting stuck and starting over again. Run. I get $/ heap attack 1. All right, let's see how this works. Good, it crashes with B, C, D, E, so that's what I wanted. Now, I gotta put in, I really only need a breakpoint. Actually, I don't need a breakpoint at all anymore. I'm gonna make a real attack. All I need to do is know what address to put in. So now here where I left off was to disassemble winner. So this is my target, and now winner starts at an address I can use. It doesn't have zeros in it. That was the only problem. So I'm gonna copy that address. Now I'll do copy heap attack 1 to heap attack 2, because as you probably remember, I very often mess everything up, and then I wish I could go back to the previous one that worked and try again. So I learned to always make many versions.
Did you have to know winner because you had the source code?
Yeah.
Or did you get it from?
Yeah. So I wonder, there probably is some command that will show you the name of every module. That's your, I know you can do it with objdump, I think. And I probably is some way to do it inside GDB too, so that would certainly help. You're quite correct. Anyway, I know a real disassembler like Hopper or IDA will totally do that. It'll give you the names of all the modules. And that's important for this reason. So I'm sure you can do it in GDB too. Just have to Google how do I see the name of every module. Probably something like that map, but I don't know the command. It's actually more complete if I figured it out and edited it to the projects though. Anyway, this is something I've learned to always do. I cut and paste in the address I'm trying for because I often make mistakes. And now, if I put that address in here, backwards and in hex, everything should be fine. So it's 7B, 84, 0408, good. This is what I'm used to, 04 and 08. So that should be that address backwards. And so now if I do heap attack 2, it should hit that. So let's just go back here and run there. Heap attack 2 and start it from the beginning, and you get level passed. So it works. Then it crashes, of course, because I've left this thing all fouled up. And we'll get to in later projects where you can actually clean things up and not crash. But the time being, it's good enough to pass. Now I was able to control the instruction pointer and go somewhere. And that's why in this contrived example, it's very easy to see how the heap overflow works. It's exactly the same as the buffer overflow back where you overflowed one variable into another. So this one is such an extremely simple example. It doesn't even really use anything about the structure of the heap. It's just two objects in memory where the first one leaks into the second one. So real pros might not even like to call this a heap exploit. Yeah?
I gotta tell you, I've been struggling with this chapter quite a bit.
Yeah.
Can you articulate the exact mechanism that has the instruction pointer gets loaded while we're doing this buffer overflow?
Yeah, yeah. Oh, it's very...
I get it when you put it on the stack, then you pop it into the instruction processor.
Yeah. And this one, yeah, I can do it. And so that's of course why we're here. So right here is the code. It happens right here. This tells it to take an address from that structure and execute it as code. That's exactly what that command does.
Okay.
So that's why this is a very contrived example. It's so contrived that it has nothing to do with the heap at all. The same thing could happen on the stack. It's exactly like that bash thing, where I have a variable I'm going to execute as a bash command, and you can just override strings into it. And then the program explicitly runs it. Okay, so this one is really not even that interesting, but it's just to get you started. The next one is more like it. So here's the way the heap works. It has these data structures, and so these are all of different sizes, and since it's not an array with fixed sizes, it does it with pointers. Each one of these has a pointer to the previous chunk and a pointer to the next chunk. So it has a list. This is called a doubly linked list. So you can start at the start of the heap, find the pointer to the next chunk and go there, find the pointer to the next chunk and go there, and they call that walking the heap. And if you have a Cisco routers use heaps a lot, and they have a process called check heaps, that every few seconds it walks the heap to see if anything's wrong. Now, if anything overflows, you will break this structure. If there's too much data here, it will override these pointers, and now you can't walk the list. You end up lost somewhere. And so check heaps in a Cisco router checks every few seconds to see if there's anything wrong with the heap, and if there is, it just throws away all the packets and reboots. Because Cisco routers are no error handling at all. Because the purpose of them is, no matter what goes wrong, just keep the traffic flowing. And if you have to drop some packets, it doesn't matter. So you get a divide by 0, I give up, I restart the router and continue. Most things will do something more complicated than that. So,
Are those pointers
yeah.
conventional pointers, double words?
Yes, there's a usual length, 32 bits or 64 bits. Just the same kind of pointer you'd make in your C code. And so you can write, that's how heaps are made. And there'll be unallocated stuff out here, and I think you'll have a special entry here saying it's the end of, a special value here saying it's the end of the heap. So you'll have an allocated space. Now, one thing that can happen, of course, as you keep allocating chunks and then deleting chunks, is you'll get a fragmentation problem, where you have a bunch of little holes and you have a big object. And so then you have to sort of clean up the heap and stuff, and there are allocation procedures to try to avoid leaving too many big holes. Anyway, so that's the one we just went through. And so this is there's the exploit and the crash. There's crashing in GDB. And there's the exploit that gets you to level pass. We just went through that. And that's your first homework on the heap, which really is just only got the passing involvement of the heap. So next one is this. Normally, if you overflow something on the heap, you do not get control of the IP. We had to have a very contrived situation there where it actually fetches a pointer from the heap and uses it for the instruction pointer. That is not normal. Whereas remember, on the stack, that is completely normal. When you return from a subroutine, you do take a number from the stack and put it in the instruction pointer. Heaps don't do that. But what heaps do is when you free a chunk, they do some write operations to hop over it. Consider if I have these 3 objects on the heap, and then I call free on this one, then this pointer to the next object has to be changed to point over to here, and this pointer to the previous object has to be changed to go over to here. So think about what happens. I have to write a value here that points over here, and I have to write a value here that points back there. If I was able to overflow something, I'm going to get the ability to do an arbitrary write. I have to write data here that comes from another chunk, and have to write it to an address that can be under my control. So now you're not going to get control of the instruction pointer, but you are going to get the ability to do one write, where you control the data and the target. That's what you always will get with heap values, even if people are not doing something stupid like jumping to pointers that are on the heap. If it's just any kind of data in there, this free operation has write operations, and if I was able to overflow things, I'd be able to control them. So now, suppose all you can do is a write to memory. Then, how can you take control of the machine? Well, you must write to some memory that will then be used as an address later. And there's a bunch of them. You could go to the return address on the stack, for example, figure out where it is, use your heap exploit to change the value on the stack. You could go to the global offset table, which is what I usually do. It turns out, you've noticed that every time we recompile programs, they have different assembly code, so they keep changing the compiler. The operating system is also constantly putting on patches. So if we just had fixed addresses for C library code, it would mess up. In fact, everything goes through 2 levels of indirection. There's one level of indirection under control of the compiler, and that jumps into another table, which is under control of the operating system. So if you want to call a system routine, you call one offset table that calls another offset table that calls the routine. And then you can put on a patch and the patch will fix the system's offset table, and your code will still work, and you can upgrade your compiler and recompile your code, and your compiler will find an offset table it can use to still hit the right thing. That's how it works. So the one that's under our control is called the global offset table. So you could change any function, any C library function like printf or scanf to go, if you write on that address, then when you call printf or scanf, it'll run that code. You could also shoot for the destructors. When you launch main, it creates some objects, and when you're all done with your program and you quit running main, it destroys those objects and it calls these destructors to do it, and you could overwrite that, and then when the program exits, it'll jump to them. You could also hook C library functions in other ways. So those are things we go. There's also something called an add-exit structure, which I've never used, but it's another object which is called it when the program exits. And in Windows, by the way, especially old version of Windows like Windows XP, it turned out that the structured exception handler was always at exactly the same address. So you never had to hunt for it. And the exception handler is what handles crashes, like divide by zero, attempt to access memory out of range, and stuff like that. If you don't have a handler, these will just lead to a system message, like Dr. Watson or the blue screen of death. But you have an option to put an exception handler in your program so you will handle the error instead of letting it crash back to the operating system. And if you can write to those addresses, then when you trigger an exception, it will jump to the code you injected. So anyway, those are common ways to take over. So let's take a look at Project 8. And that's my plan here. So Project 8 is a more realistic heap overflow. This one was so simple, you don't actually learn much about the heap. This one here, however, is a classic one where you're actually going to use the heap. So I've got this curl nonsense again. And for some unknown reason, I have to execute these outside the virtual machine, but that's all right. I'm happy to just use anything that works. So let's run this. Now I get heap1.c.
Try PB copy this time. If you
What's
want.
that?
There's a command line tool that you can cast something directly to your clipboard.
Yeah, I don't know. I'm not a very.
You can try this. It's just cast the file and pipe it to PB copy.
Yeah, it could be. I'm gonna happy to just use this that works now. I'm gonna go down. This goes down to I2.
That's the first line.
Oh, I did miss the first. That's not gonna work. Thank you. Okay, let's get the code. Okay, let's go to the end of L2. I'll work. I'll use this because it will read to the result. I'll get out of here. Quit. Nano heap1.c. I don't know what you're gonna call heap1.c. Put in that junk. Okay. Go back to here and see what else there is after the 3 lines of I2. Okay. There is this junk. All right. All right. So let's take a look. I don't know if I have slides about this or not. No, we're just, okay. So let's take a look at my project instructions here to get all right, here's what we got. We're now going to create a data structure. This is the right one, right? Yeah, okay, good. All right. Again, it has an integer and a pointer to a string. We want to execute this winner. It's going to create some objects called structure internet. Now, the internet structure just has an integer and a pointer to a string. We are not going to all right, so now I'm going to allocate one object, allocate another object, then copy the 2 arguments into it so I have a chance to overflow, then leave, and when I leave, it's going to automatically call free. I think that's the point here. So that's the game here, and if I have one object that runs into another, it's going to end up overriding it. So let's give it a shot. See if that looks like the right code here. There's my internet object, just 3 pointers, and I allocate one and allocate another. Okay, it didn't even call free, but I guess it must be calling free automatically. All right. So let's compile it. I don't know if I need any special compile switches. I'll just use them here. So there we are. It'll run with short things, fair enough. Okay. And my copy function doesn't work very well in Chrome. Everything's sort of broken. You get used to it. All right. There we go. All right, so now I can call heap A and B, and that works because the objects are small enough to fit in there. But if I make longer ones, then I get a seg fault. And this is where you begin to get a little bit more fun learning how to exploit things. So let me GDB, and let's get my attack string in the clipboard. Okay, now I'm going to run. Okay, so it crashed. Now, when it crashed with a seg fault, and did not apparently put anything good in the extended instruction pointer. I just have some kind of library code I died in here. But if I do info registers, I see 42, 42, 42, 42 in EAX. All right. Now let me go back and get the exact one from here to make it simpler. This one was all E's. Tried various things. All right. So here I get seg faults. I found out what the minimum was: 4 A's, 4 B's, C, D, E, and F. 4 of each of A, B, C, D, E, and F. All right. Now, what I want to do is run that thing. Let me get this string in my clipboard. I just put both of them in the clipboard. All right. Because that should give me 2 interesting results. So let's run. There we go. All right, now info registers. Yes, now I control EDX. That is full of 46s, which is what? A, B, C, D, E, F. That's Fs. And this one is full of 47s, which is Gs. Now it looks like I only have 3 47s, not 4,
Yeah, it pays the mix.
which is a little strange. But anyway, I guess I need another letter there. So this may not exactly be matching my case, but let's put FFFG. Let's put H's over here. There. See what that does. All right, now EAX only has 3 of these.
What if you put another G? Sorry, H.
Yeah, possibly, but the G should have gone in there. Anyway, let me go back and see what happened here. Something's still a little bit off here.
So you have four Gs.
I do need to control both of them, and they should be adjacent to each other. Anyway, let's take a look at the extended instruction pointer, which you can do by examining in X 2 instructions at the EIP. All right, the point is, this is the move instruction that caused a crash. It's trying to move EAX into the address pointed to by EDX. So if I can control EAX and EDX, I can control both sides of this move, the data and the pointer. Now, the only problem is I seem to be unable to control 1 byte of EAX here for some reason, and that's annoying. So let's make a simpler attack. Let's just have all A's. Let's have a lot of them. There, that's going to be enough. And IR. And now I should only get 3 bytes, 62, 62, 62. How rude. I see. I see what you're saying. It's these that go in EX.
Yeah.
It's the second object. Oh, thank you. Good. Well, see,
Yeah, I wonder why it was 3.
well, I was lost. Good, thank you. All right, good. Now I feel better. Okay. So it's that right there. I failed to copy the last byte. Oh, good. Well, see, when I'm doing something stupid, be more vigorous in explaining it. All right. All right. I say, I used to be a student, and I wondered why my teachers were so stupid. Now I understand. So, all right, that looks better. Now I run it. Now I do info registers. There we are. So the G's go in here, and the D's go in there, and the instruction, now I'm on track. EIP. All right. So it crashed. This is the instruction pointer, that little arrow. So it was unable to do this operation because it was trying to put that value into this memory address, and that's an illegal memory address. So now I can put any byte anywhere I want to in memory. So I just need to choose a target and decide what value to put in there. Now the value is pretty easy. I just disassemble winner. There's this winner function I want to run. Okay, so that is the value. So let's build an exploit here, like we did before. Like this, nano heap attack 2. Let's see, heap 1, A, all right. should have a more consistent naming scheme, but it's too much bother. Okay, this is the address to jump to. Okay, I'm just trying to save all the information in my code so I can easily find it. Okay, now the other thing is, where do I want to write to? And to find that, the easiest way to find the global offset table is with obj dump. I think it's obj dump minus D. Let me check my instructions here. Yeah, obj dump minus R for relocation. Okay, so let's go back. I'll just open another window. Okay, and okay, so there's my heap 1, so I can do obj dump minus relocation on heap 1. And there they are. This is the global offset table of this program. It goes to printf, time, stir copy, malloc, puts, and here's the addresses where it puts them. So I just need to choose which one to target. Now, to do that, let's disassemble main. Okay, so here it does allocate and allocate, so this is not interesting yet. Then here it does the string copy. This is what's going to overflow something. And then eventually I'm going to get down to where it crashes. Here's another string copy, and here's a puts. Now I need to figure out, I think all I care about, this is the puts that's going to print some kind of message on the screen. So it does that after it's all over. So I think all I have to do is target puts. So when it executes this instruction, it will go to the page I put it. I think that'll work. So I just need to know where puts is, and that is here. And I could choose any function that is called after the heap overflow, and it would do. So that's the missing information to make my attack, and that goes here. Another comment there. So that's the information I need. So now let's plan my attack. Up here in GDB, the attack I did was this, and the F and the G ended up someplace good. Let me just save this attack and put that in comments there too, just so I have all the information I need here. Okay, come on. All right, I missed the G again. All right, so let's run this again. Yes, and then X2I, and then info registers. Okay, it is, all right, I fouled it up again. What did I do? That's right. Yes. Info registers. Yeah, okay, there we are. EAX is 47, EDX is 46. Okay. But I didn't end up at the right, so now what am I doing wrong? Eugenius is out there. Let's just try getting out of this and coming back. I never learned how to leave this program. Okay. Heap 1, run, and the attack string is here. Okay, I don't need any breakpoints or anything. X2I. Oh, X2I EIP. Oh, I might have forgotten the, there we are. I was not putting in the right register. Okay, good. No, here we are. Guys, so it's move AX to EDX. Okay, right on track. Now info registers. Okay, come on, info registers. There. Okay, so this is the command, move EAX into the address EDX. EAX is the 47, the G's, and EDX is the F's. You just have to avoid getting it backwards. So the second argument is the value, and the first argument is the address. Let's give it a shot. So the second argument is that. So I need to take my attack string, which is here. Okay, there it is, and I need to modify it. So it is print this. All right, so it is A equals this, Okay? Then A plus equals, okay, and this is going to be the value. All right? I'm just going to do it. I'm too tired of worrying about it. We're going to get right or wrong. So it's this is going to be backslash the first one, AB, because it's easy enough to flick it later. 84, 0408. Good. It's almost always 04. Okay. So there's one of the values. Then I want to put the other one down here with a space in front of it, because that's the second argument. And the other one is 9098. The address of puts. Okay. And 04 right there. So there's an attack. That's either forward or backwards, because I can never make the binary keep it straight in my head. So that attack string, which is H1A.
I remember to print A. You didn't print A.
Oh, why thank you. Good. That's important. All right. Let's put that in. It's certainly not going to work without that. Okay, print A. All right, good. Now let's run it. All right, good. So it prints that junk, and then it prints some binary junk that won't print right, so that might be right. So let's run that. H1A. All right. Starts at the beginning, and it crashes somewhere doing something horrible, which...
The dollar sign should be outside of the parentheses.
The what?
The dollar sign should be outside.
Oh, it should. I thank you. That's garbage. Thank you for telling me. Good, good. Thank you. All right. And now it crashes, and it didn't print that I won, so I probably just got it backwards. So if you're motivated to think, you could try to figure it out, but I'm more motivated to try it this way. Put them in the other way. There. Now they're the other way. One of these might work, and if not, then I have to think. All right. There, that should do it. Yes. And we have a winner. So that's it. I hope it's not too confusing. This is very often when you have to choose something, it is far faster to just try both than to torture yourself through the logic, at least the first few times. All right, so that's the game. So now what I've done is I've done the same thing, and this now depends on the structure of the heap. By having one object overflow, when it tried to create the next object, it tried to use some pointer from the existing object, which was corrupt, and somehow it made it arbitrary right. I didn't even have to call a free to do it. So you got a variety of these. There's project 8x and project 5x where you do this stuff. So first you do the simple heap overflow, which doesn't even have much to do with the heap. Then you do the second one, which has a little more to do with the heap. Then you can start having fun, which is 8x, remote shell, and 5x with a similar one. And I think I got all these from the same capture the flag a couple of years ago, which were a lot of fun. So here's, there's my server. One of my servers is running this thing on port 8010. And so you can get a local copy of the code to analyze if you like, and you just have to exploit it. So feed in stuff, you can look at the code and figure it out, or you can just feed in longer things until it crashes and try to figure it out, but you normally have to have a local copy to run in the debugger to really get anywhere. So this is intended to make it easy. You actually have the C code to look at if you want to. But in real viruses and stuff, you don't have, all you have is the compiled code, and you have to work from that. So give it a shot. The same procedure should work. It's just a slightly modified version of the same program. And then there's a similar one here, which I was just mentioning. Remember, all the ones we're doing here, it prints it's a winner, and then it crashes because we trashed registers and stack and not fixed them. Here's one where you have a canary, and you learn how to overwrite the canary. So again, you can see the source code. You get the binary, but you don't get the source code. But you'll find here that the stack has a value. It writes something there, and it checks to make sure it hasn't changed. But it isn't a random canary, so you just have to correctly write it, and then it will not detect that you have overwritten the stack. So it's you have to be a little bit more careful. And this is how you avoid crashing things too. When you overwrite the stack, at the end of the stack frame, there's the instruction pointer and the extended base pointer. And you have to put in the right extended base pointer, and then it won't crash. So you just have to repair all the damage you do. Anyway, that's what I wanted to show you. And I think I'm out of slides and everything. Do I have any eye clickers? I do. Let's do some eye clickers then. Got a bunch of them. And a few of these review last week's stuff. So grab an eye clicker if you need one. And that's the last thing we're going to do in lecture today.
Oh, God.
That's right. You broke the eye clicker. All right. Let me need this till later. All right, there we go. All right, let's get rid of this and get to this. There we go. All right. Start this crazy thing. Okay. So, be sure and throw your eye clicker on the floor a few times to warm it up and be all set. So, all right, what's wrong with that program? All right. Guess I'll wait till 50 and we'll find out how many voters there are. What's that? I can't hear you. All right, anyway. All right, that's got a format string vulnerability. Not the most popular answer. All right, so let's talk about it. Right there, printf name. It prints something which came from argv1 without a format string. You're supposed to do like printf percent quote percent s end quote then name. So right there you can do format string attacks. There is no buffer overflow of any kind because you reserve 10 bytes and then you copy only 10 bytes into it with this 10 argument here. So there is no overflow. It's just that you print something without a format string and that makes it possible to take over the machine. We went through that before. All right. How about this one? By the way, that previous format string vuln would be hard to exploit because you only have 10 characters, but you could at least make a DOS exploit. Probably couldn't really do much more than that, but you certainly could do a little bit of damage. All right, I think I'll quit at 45. I think 11 is probably as many as I'm going to get. All right, and the answer is D. There is nothing wrong with that program. E is a debatable answer. Someone, whoever is voting E, you're holding your eye clicker upside down or something. Anyway, but there's nothing wrong with this. There's no overflow because you reserve 10 spaces, you copy 10 bytes, there's a format there when you print something. There's nothing wrong with this program.
I would argue E is too if I had done it.
Yeah,
but I did.
I would argue E.
You think, well, you're going to have to make a pretty good argument for E. So, all right. Okay. So, how about this one? Let's see. Oh. All right. What was that? Oh, I see 11 votes. Good. I'll quit at 30. All right. Oh, 12. Okay. Well, anyway, I'm quitting at 30. All right. So that is a good old Stack Overflow. Good. A popular vote. Somebody's still voting E. This must probably Duffy. He's the one that would do that. Anyway, so here you take a command line argument, and here you copy it into a thing that only has room for 10 without limiting it. So that's a classic Stack Overflow. This local, by the way, I should mention that in practice, this one is very hard to exploit because the process of returning from main to the operating system is complicated, and it's not as simple as finding EIP just right there. But it's got an overflow. That's why I had real trouble developing these projects until I went through Georgia Wiebben's book, and she had a simple example, and I realized you always make the overflow happen in a subroutine. And then it happens just like it should. If you put it in main, it's real hard to exploit, because main has a complicated data structure to jump back to the OS, and it's harder to understand where the heck to put in the code you want to control. Anyway, so, all right, let's have another one. What's going on here? guess I'll quit at 30 again. Looks like the answers are in. One more to come, which is going to be Duffy voting E probably. All right. So this one is format string again. Not the most popular answer. You go on the heap and you allocate 10 bytes of space, then you put only 10 bytes into it, but then you print something without a format string. So all this is misdirection. Nothing's wrong up here, but that one line is wrong. So that's a format string vulnerability.
Just saw the vocabulary word from this week.
What's that?
I just saw the vocabulary word from this week and got excited.
Oh, yeah, yeah. All right. Yes, that's true. Well, anyway, how about this one? All right. Looks like I can quit at 30 again. All right, so that is the one you came here to see, the heap overflow. Because you allocate 10 bytes on the heap and then you copy an arbitrary amount of junk onto it. So now you actually overflow something on the heap. Again, it's going to be hard to exploit because without another heap object next to it, you're not going to do an arbitrary write or anything, but it does have the overflow. So you're able to create some degree of memory corruption. It, as we found out, I don't know, Ben's not here anymore. Ben spent a long time fuzzing and finding all these bugs and then not being able to exploit them because there's a lot of memory corruptions that don't actually lead to anything under your control that's any use. Like you just fill memory until you hit the end of some segment, and that's really no way you can take over the machine with that. So that's the breaks. All right, so what's the format string that displays memory in hexadecimal? A few things from last week. All right, looks like I can quit at 20 or 25. I think there are 12, 11 or 12 total. All right, %x does that. Prints out hexadecimal. Good. All right. Which format string writes to RAM? Which is the entire reason why this exploit works, and I have no idea what the legitimate purpose of this is. The only value of this format string I can see is to hack into things. I'll quit at 25. That's %n. %n writes to RAM, and the value it writes is the number of characters you printed so far. I'm guessing this might have something to do with formatting data to wrap around on your terminal or something, but anyway, it's pretty strange. Anyway. All right. So which one of these runs when main exits? What's that?
There's 5 answers.
There are 5 answers, yes. I'm going to quit at 30. All right, and that's the destructors, the detours. They run to clean up when your program is over, so that's a place you can put an address, and the code at that address will run when your program leaves. All right. Which one of these do you use to exploit simple stack overflows? All right. I'll quit at 30. All right, and you use the saved return address. That's the classic Aleph null type exploit. Overwrite the entire stack frame and change the return address. All right. All right, which one of these is particularly easy to find in Windows? at least older versions. And we'll be doing this in a couple weeks when we start exploiting Windows. All right, that's the structured exception handler, D there. A handy target in Windows. All right, yeah.
Web Workshop, like, so I see is using that in SQL injections too a lot. Is
The exception handler?
well, kind of, yeah, on error. So
You create an error with SQL injection and then you,
well, yeah, create a no image, like image equals blank, and so that creates an error and then on error. And
Oh, okay.
put in your injection there.
oh, okay, well, that's fine. Yeah, you have to create an error somehow. SQL injection is one way to trigger the error, yeah. Because of course, this does leave you with another problem. If you overwrite the SEH, now you have to trigger an exception. So those are two problems you have to solve.
Right.
Okay. All right, good. All right, so which byte causes execution to continue, changing nothing? I say when I started, I memorized the numerical codes of instructions, and there's a few that are still worth learning. I'll quit at 30. All right, and that's 90. 90 is NOP. Does nothing, so you can put 90s in to make your NOP sled. Which one stops execution immediately? And you use these things all the time to test code. You know, we're injecting something, you put in some of these bytes to cause simple consequences that you can see in your debugger, or even outside it sometimes. Quit at 30. All right, that is CC, which is int C. That breaks right where you are. Not a popular answer, but it's true. All right, yeah, CC is int 3, which stops. It's break. So code will stop. So one thing you can do when you're putting, if you aren't sure whether the area you're exploiting is executable and you don't want to bother looking up instructions, just fill it with CC, and if it is, it'll break and stop right there. That's why, that way you don't waste your time further trying to exploit something that's not executable or that you can't get to. Anyway. All right, and the last one, which byte terminates a string, which will generally foul up your shellcode? The reason why I can't use my Kali 2016.2 anymore. It would be sort of nice if somebody would figure out what they did wrong in Kali 2016.2, but it seems to be pretty bad. It's fouled up several of my projects so far.
I think it's an update exception. So what I noticed, I'll have to go try it some more, but when I noticed there was an update exception that you have to acknowledge, and if you don't, then it just screws things up.
Oh, I don't know. Anyway, this is 0. Good, 0 terminates a string. That's a popular a piece of information. All right, so let me stop the recording and I'll see who got the most right. This was, well, that's not the right thing to stop. This is the right thing to stop. There, this is 127, chapter 5.